I'm of the opinion that anyone who spends a non-trivial amount of time talking about complex numbers need to at least mention the Euler's identity. So the Euler's identity states the following: e to the power I pi plus 1 is equal to 0. My first encounter with this was through a book that I read when I was in high school. At that time, I was totally blown away by this identity. The remarkable thing is, it involves 5 very celebrated constants in mathematics. 0, of course, is a very important number. 1 is the building block of all counting numbers and eventually all rational numbers. Pi is a constant that has been known for a long time, and it gives the area of a unit circle. And e, known as the Euler's number, is the base of the natural logarithm. And of course, we have I, our imaginary number. Even though I was amazed by this identity, there were some doubts that I had. What does it really mean to take e to the power I pi? But that question was never really settled in my mind until I took a complex analysis course in university. If you search for Euler's identity, you will see many videos and resources giving a proof of this. And what you might not notice is many of them do not acknowledge or point out the subtlety involved in proving this identity. So let me show you a very common way of arriving at this identity. And this is known to be the way that Euler arrived at this identity himself. And the key is the following. So the power series expansion of e to the x is given by 1 plus x squared over 2 factorial plus x3 over 3 factorial and so on. So the generic term is x to the n factorial. So if you take e to the ix, what you end up with is 1 plus ix minus x squared over 2 factorial minus ix cubed over 3 factorial plus x to the 4th over 4 factorial and so on. And now you can write this as 1 minus x squared divided by 2 factorial plus and so on. And then plus I times x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial minus x to the 7th divided by 7 factorial and so on. And this thing here is the power series expansion of cos x, and here is the power series expansion of sine x. This might look convincing at first sight, but there are a few questions that need to be answered. So first of all, what is a power series expansion? Right? How do you really add infinitely many terms? This is a question that is answered in an introductory analysis course. And once you have established the meaning of a sum that involves infinitely many terms, you can ask the same thing. Okay, what if this x is a complex number? Does this infinite sum still make sense? And if so, in what sense? The other thing is, can you really do this? I have split this infinite sum as the sum of 2 infinite sums. Now, if there are only finitely many terms here, this is not a problem. But again, because we have infinitely many terms, the precise meaning of this operation needs to be carefully defined. And once you have taken care of all those details, then you can conclude that e to the ix is equal to cos x plus I sine x. And now if you plug in x equal to pi, you get Euler's identity here. This of course is not the only proof. As I mentioned, there are many different proofs. But to write down a completely satisfactory proof, one really needs the machinery of modern calculus.